Today we're going to look at section 5.8, which is on analyzing graphs of polynomial functions. And our goal is to use intercepts to graph the polynomial functions today. So the zeros, factors, solutions, and intercepts. All of those things really give us the same information. So if we take a polynomial function in standard form, the following statements are equivalent. The zeros, it says k is a zero of a polynomial function. If k is a zero, that also means that it is a solution, just like the third statement there. K is a solution to the polynomial equation. If we're looking at the graph, that means it's an x-intercept of the polynomial function, and it crosses at whatever your value is. So the zero, solution, and the intercepts are all really the exact same thing. Now the factor means that if k is a factor, then we'd have x minus k. So if 2 is a 0, then x minus 2 is the factor. If negative 7 is a 0, then x plus 7 is a factor. So our goal is to look at example 1 and to use the intercepts to graph a polynomial function. Again, remember the stuff that we talked about in section 5.7. If this is an even number, an even exponent, that means it has to bounce off of the x-intercept. So we know that 1 is one of the intercepts. And I'm going to put a dot there because I know it touches it and turns around. Okay, it touches it and it turns around. It will not cross there. It will just bounce off of there. It is tangent. Here, in the first one, this is a negative, or is a 1. It's x plus 2 to the first power. That means it is going to cross at negative 2. So here is a point that's an intercept, or a 0, and it's going to bounce off of our graph. Now, if we look at this, this is a third degree polynomial. Because if I would multiply these out, it would be to the third power, so that makes it odd. And it's negative. So if it's odd and negative, I know my end behaviors are going to be here and here. So now really all I have to do is plug in a couple points, and I can see in a hurry what's going to happen to this graph. So I'm going to put in 0. So f of 0, I'm going to put in 0. That's going to give me negative 2. 0 minus 1 is negative 1. Negative 1 squared is 1. So that's going to give me negative 2. So I have the ordered pair 0, negative 2. Then I also have, I'm going to put in negative 1. If I put in negative 1, I'm going to have negative, and then I'm going to have 1. And negative 1, that's going to be negative 2. Negative 2 squared is 4. So that's going to give me negative 4. So if I put in negative 1, I'm going to get negative 4. And then I'm going to also put in well, let's try f of 2. And so that's going to be negative, and that's going to be 4, and that's going to be 1. So that's going to be also negative 4. So if I put in 2, I get negative 4. And so I can see here that it's coming down to my end behavior on this side. And then now we get to here. We could put one more point in, but we made quite a jump here. So it's going to be going to its end behavior up there, because we know it's never going to cross that x-axis. Here we knew that it was going to bounce off it. Here we knew it had to cross it because of what we know from there. Okay, so that's how we would graph that problem in example 1. Well, the next thing we're going to look at is something called the turning points. And the turning points is the place where our graph changes direction. And so we're going to talk about two different types of term. The local maximum, well, obviously the maximum means the highest point. However, we're going to have local maximums and then local minimums. Okay, so it's the highest point of all nearby spots and the lowest point for all nearby spots. So when we look at the turning points of a polynomial function says this, that the graph of every polynomial function of degree n has at most n minus 1 turning points. So If it's a third degree polynomial, the most turning points it could have is 2. If it's a 25th degree polynomial, the most turning points it could have would be 24. It's always one less than the degree. That's why a line has no turning points. Quadratic equation, a parabola, has only one turning point. And the cubics will have 2. This one we have graphed above here is a cubic function, and it has 2 turning points. That's the most it could have. It doesn't have to have that many, but that's the most that it could possibly have. And 2 says if a polynomial function has n distinct real zeros, then its graph has exactly n minus 1 turning points. And so if all the n, or if the n has n distinct real zeros, then its graph has exactly n minus 1 turning point. Meaning if we don't have any imaginary ones, then it must have that many turning points. So example 2 says find the turning points. We're going to graph the function x to the fourth plus 4x cubed plus 3x squared minus 4x minus 4. So what we're going to do is this. We're just going to plug it right in on our graphing calculator. So pull up your graphing calculator. And again, I'm going to go to y equals. We're going to clear everything out, and we're just going to type that in. Again, here is the equation we're going to type in. F of x equals that. So go ahead and put that into your graphing calculator quickly. All right, so if we graph these on our graphing calculator, here is the graph that we would get. Now, if we look at this, we can tell from our graph that our x-intercepts occur at -2, -1, and 1. So those are the first things that we're going to look at, the x-intercepts. They ask us for those. So the x-intercepts are at -2, -1. I think that's what they were, right? -2, -1, and +1. Okay, so there are my x-intercepts. They also want to find the local maximum and the local minimum. So we're going to want to find those ordered pairs. And again, if we go back to our function, we're going to look on here. The local minimum is going to occur right there and right here. And our local maximum is going to occur right here. So it's the point where our graph changes the direction. It's the highest point or the lowest point. So we're going to do this the same way that we did the other day of finding the zeros. And in this case, we could do it the same way, but we don't have to in this example because we can see that they cross or touch the x-intercept at -2, -1, and 1. So we're going to do the same thing. We're going to go to trace, second trace, calculate. Now, this time, instead of finding the zeros, we're going to find, and let's start with the minimum. And again, we're going to do it exactly the same way. So we're going to hit left. Got to go to left of this minimum value right here. And so I'm going to hit enter. Now I'm going to go to the right of where it changes directions, hit enter, and find the point where I think it is, the bottom, and hit enter. And then there they give it to us. It is -2, 0. Well, that makes sense because that is our point where it switches direction. -2, 0, that's the intercept in this case. Oops, sorry, that's not the local max. That's one of the local mins. So -2, 0. Then if we want to find the other local minimum, we're going to do the same thing. Let's go to second calculate or trace, and that's the calculate button. And I want to find the minimum. But this time, let's go to find. Oh, messed up there. So let's go to find the minimum. And I have to go to a point on the left. So here's a point on the left of the minimum. Here's a point on the right of the minimum. And then we're gonna, right there, it looks like it's pretty close. And so it's gonna be negative 0.37, or sorry, 0.37 and negative 4.85. So we're gonna have two local minimums. And then we also need to find the local maximum. So if we go to the local maximum, now we're going to look for that, doing exactly the same thing. Just got to put the marker down. We're going to go to second and hit trace again. And now this time we're looking for the maximum, which is number 4. And again, you have to go to the left side of it because it says left bound. So we're going to pick a point on the left side of that maximum. And then on the right side of the maximum. And now I got to try to find where it is. Hit enter. And it's going to be negative 1.37.35. So the local maximum then is negative 1.37.35. Okay, so that's how you're going to use your graphic calculator to find where the x-intercepts are, and also the local minimums and the local maximums. In example 3, we're now going to look at a word problem. So we're going to be looking at making a rectangular box out of 12-inch by 15-inch piece of cardboard. The box will be formed by making cuts and folding up the sides. You want the box to have the greatest volume possible. How long should you make the cut? So if we look at our box, here's our box. We're going to make cuts out of each corner and fold them up. And they say that this is 15 inches and this is 12 inches. So these are going to call X. So how long should you make the cuts? Well, we want to figure out what this function should be. Well, we know that the new box, we want to find the volume. So the new box should be 15 minus 2x by 12 minus 2x times x, and that's going to equal our volume. So we really want to find out what x is going to be in this case. So we're going to multiply these. So we're going to FOIL the first two. I have 180 minus 30x minus 24x plus 4x squared. We have the x left. I'm going to put my like terms together right away. So I'm going to have, and I'm going to write it this way, minus 54x plus 180 times x. And so v is going to be 4x cubed minus 54x squared plus 180x. All right, so there is our equation for the volume of this polynomial function. So now what we're going to do is we're going to put this into our graphing calculator. So you're going to go back to y equals, you're going to clear that out, whatever we had in there, and we're going to now type in this new equation. So the volume we said is 4x cubed minus 54x plus 180x. Oh, 54, that's x squared. So let's insert x squared there. So we got 4x cubed minus 54x squared plus 180x. And let's graph it. We'll see what our polynomial function looks like. Well, that does not give us a very good idea of what our graph is. So let's zoom it out. And we still don't see where our goal, remember, is to find the maximum volume. So if we're trying to find the local maximum, we got to get this point in here. So let's zoom out again. We'll see if that is going to give us our local maximum. All right, we still don't have it on here. I'm going to go in here and change my window to see if I can make it give us a better idea. We know it's somewhere between, I'm not going to change the x. I'm going to go -5 to 5, and we're going to go 0 to, let's say, 100. Let's go 200 just to see. Okay, so now let's graph this. See where our graph goes, if it's going to cover that. Okay, so, and you can keep zooming out until you find whatever that is, but now I just want to find the local max. So again, I'm going to go to second to calculate, and I want to find that maximum. And I'm going to find a point here on the left. Point on the right. And the maximum value. And it tells me it's about 2.21 and 177.23. So if we write that point in here, the local max is approximately, what did we have there? So 2.21 and 177.23. Okay, so that's our local maximum. Now, question A says, how long should you make the cuts? Well, it's going to be approximately this. That's what X represents. So approximately, or about 2.2, what are units? Inches. So we want to make it about 2.2 inches. Now, what is the maximum volume? Well, the maximum volume is going to be there. So the maximum volume is about 177 cubic inches. And then they're asking us for the dimensions of the box. Well, now we just plug it in. So the dimensions will be about 2.2 inches tall by, and if we put those numbers in, put 2.2 in for X, then we're going to get by 10.6 inches, and the other one is going to be 7.6 inches. So the dimensions of the box will be 2.2 tall, 10.6 long, and 7.6 wide. All right, so here are some of the guided practice questions. We're going to do, let's do the first two together, and then I'll give you a chance to look at a couple of those. Again, because we want to look at what happens here at some of these points. So first of all, I know that this has 3 zeros. My factor is x plus 2, so I know that negative 2 is a 0. It is an odd, so it's going to cross. 1 is a 0. It's going to cross. And 3 is a 0. It's going to cross there. I know that it's odd and that it's positive, so I know my end behaviors are going to be there and there. So now all you have to do is put in some points. So if you put in 0, and I already did some of these, so I'm just going to plot some in here. You're going to get somewhere around 1.5. If you put in 2, you're going to get negative 1. If you put in negative 1, you're going to get 2. And then if you put in 4, you're going to get a number and it's going to jump up. So we know that it's going to go up here, cross there, and cross here. And so those are your end behaviors. Now, they ask in this question to identify the x-intercepts. Well, the x-intercepts are easy. The x-intercepts are negative 2, 1, and 3. Okay, so that's what you would write for your x-intercepts. The local maximum in this case is right here, and that is the ordered pair negative 1, 2. The local minimum occurs right here, and that is the ordered pair 2, negative 1. So using your minimums and maximums, find those things out. Now, example 2, you have a 0 at 1. However, that's an even one. So that means it will just touch that and it'll bounce back. 4 is a 0, but that only occurs once. That's an odd exponent, so that is going to cross. I know it is, again, a cubic. There are 3 zeros, or 3, it's x to the third. So it's going to be odd and it's positive. So I know that, again, my end behaviors are going to be there and there. So it's going to do something like this and cross and go up. It's going to go down this way. And then it's going to bounce back up here and go back down. Okay, so there's the general graph of what that's going to look like. So again, the x-intercepts, 1, 0, and 4, 0. Then they ask us for a local maximum and a local minimum. Well, the local maximum is, again, right here at the vertex. Well, and we don't know what the local minimum is. You type this in your graphing calculator, you plug it in, and you're going to find that the local minimum here is going to be 3, negative 8. If you plug that into your graphing calculator. Right. So what I would like you to do now is go ahead and do questions 3 and 4, plug them into your graphing calculator, and list all of those things that it says. As for the x-intercepts, it asks for the local maximums and the local minimums. So go ahead and plug questions 3 and 4 into your graphing calculator and list those things. So you can hit pause on the video and then hit play when you are ready. And there are the answers to guided practice questions 3 and 4. I just graphed them on my graphing calculator. I don't have them shown here, but the x-intercepts for number 3 is negative 3, 0, and there's your local minimums and your local maximums, also for question 4 over there. So once again, today we talked about analyzing graphs of polynomial functions. How do you find the local minimums? How do you find the local maximums? How do you find the x-intercepts? And what do those x-intercepts mean, along with what the turning points tell us for these problems. So here is your assignment for section 5.8.